know for a fact what they said. So suppose X is I hope you'll excuse me, complex projective variety. And despite what you have seen in this workshop, this school, complex projective varieties are interesting. So N1 of X, that's a lattice. This is the image in the second cohomology group with rational coefficients of the classes of divisors. So it's some lattice in some space. So this is some lattice in the associated vector space. So this is these are the cohomology classes of up to you forget all the stuff that is non-numerical of divisors or divisor classes, and lower one is the sort of the dual, is the image of the classes of curves. So I guess classes of divisor of line bundles to kind of emphasize that this is cohomological and this is homological. In H lower 2, and of course there's the space in which it is contained. And the fact that I killed everything that is non-numerical means completely tautologically that these spaces in which these lattices lie are dual to each other. So there's an intersection pairing, and if you wish, on the rational, so this is the restriction of Poincare duality, and it's a perfect pairing. On this side, and so this is the lattice of line bundles. This is the lattice of curves, and they're dual. And of course, when we study algebraic varieties, what we learn in the beginning is we want, especially. So I should have said, yeah, I said it, projective. Projective doesn't say that it's in projective space, so we want to understand how it maps to anything, in particular to projective space, and for that we need ample line bundles. So we have a cone, and here's the rational version. This is a cone. If you take two classes of an ample bundle and add them, and then we take the tensor product of the line bundle, then it's ample. And it's a convex cone. There's something on the level of curves as well. And let me just mention that I'll be interested in its closure in a little bit. And there's something on the other side, which is just the class. So E, the n is just the same n, and E stands for effective curves. So we have two cones and kind of lattices in them. Now these cones can be really wild and weird. There are easy examples, for instance, for abelian surfaces where the cone is round and nice. But there are... Okay, so here's the fundamental theorem on these cones, and that's due to Kleiman. Which says that I guess maybe I should kind of suppress the Q's. Well, never mind. I won't. The closed ample cone and the closed cone of effective curves are dual to each other. Namely, so what does this mean? I take the class of a line bundle and I ask myself, is it in the closure of the ample cone? L is in the closure of the ample cone. In some sense, it means that its class can be approximated arbitrarily well by the class of an ample line bundle, although I took rational coefficients in order to do this. If and only if for any effective curve inside X, the restriction of L to C is non-negative. Now, this is a beautiful theorem. And, if I had the infinite amount of time, I would just sit here 5 minutes and just contemplate it. It's so beautiful.
Without closure, this Nakai-Moshizon?
Without closure, you have the Nakai-Moshizon criterion, which requires not just intersection with curves, but intersection with any subvariety, which is was proved by Nakai and Moshizon, I think, for surfaces. And I don't think they proved it in general. I think it's in Kleinman's paper that it's proven in general. Even that. And it's proven in the right way. That's another thing. It's really a beautiful proof. I'm not going to prove it. This is something nice you can give to your student as a project to fit at the end of your topics course in algebraic geometry, as indeed Brendan Hassett did 13 years ago. I guess he's not in the course I taught. So, all right. So that's Kleiman's theorem. Okay. So since we want to understand, okay, let me tie a little bit with what people have. Remember, at least yesterday, we had one lecture where it was shown that even for arithmetic problems, you take an algebraic variety, you want to understand the rational points on it, it's often the case that you want to first blow down all the junk. You have a surface, might have some -1 curves, you will want to blow them down to get something simpler. So contract whatever possible in X to get to something minimal. And in the lectures on surfaces, I'm sure there was mention on what a minimal surface is. And for a long time, the question stood, what is the right thing to do for higher dimensional varieties? The theory, or the birational geometry of surfaces was known since the beginning of the first half of the 20th century. By the end of the first half of the 20th century, Zariski wrote a book that summarizes it, and everything is proven nicely. And you can, it has been republished, so you can actually read it. But then what? You take a threefold. What do? Turns out that just like a -1 curves, the behavior of the canonical sheaf, and just like I did in this entire course, the behavior of the canonical sheaf is a crucial point. So if you have a line bundle, and so I'll concentrate not on the ample, but on this cone, the cone of curves. So remember, for surfaces, you blow up these very special rational curves, which are called you blow down, you contract those -1 curves. So the idea is to look for very special curves that will tell you what you need to contract. And one way to look at the cone of curves is to look at slices that are obtained by seeing what the canonical bundle. So we can look at this locus, which is the locus of elements in one of X, let's say Q, such that so Kx dot V is so that the class of Kx. I think of Kx as a class, right? And you can intersect it with this cone of curves. If you look at the theory, so the motivation comes from the theory of surfaces. This is explained in great detail in the book of Matsuki that is in the references of my notes. If you look at the case of surfaces, you see that all these -1 curves lie on the boundary of this cone on this side, and they lie in a nice way. And the point of this lecture is to explain why this is a general picture. So the claim is this is important, because even for surfaces, the -1 curves lie here and lie in a nice way. And we'll see in a little bit. No, let me just tell you. So the general picture is that this subcone is locally polyhedral away from the locus where So here's the picture. Let's first draw the plane Kx equals 0, the hyperplane Kx equals 0, and we are looking at it from below. So I'm thinking of it, this is it's lying here. Yeah. And here's the origin. Let's intersect the cone of curves, of effective curves with this. And then there's the positive side, which is not. Now, have they heard about colored chalks here? Well, I think I'll manage. So there's this side, which is the positive side, which I'm not saying anything about. So I'm drawing it round because it could be round. There are examples where it is round. And also the intersection with kx equals 0, I don't have enough dimensions to draw it. It could be completely round, as in some examples of abelian surfaces. In abelian surfaces, this is not, the whole space is kx equals 0, right? And now we look at the locus where it's negative, and what I'm saying is that there's a countable collection of classes of curves that they lie on this side, and they don't have accumulation points on this side. They only possibly accumulate near this plane. And the cone is polyhedral on this side, as long as you don't get too near this. It has infinite structure as you get near to kx equals 0, but with the colors, it would be a little easier to see, but I'm looking at rational, but it doesn't really matter. So this polyhedral locus, I'm saying it's generated by countably many classes of curves. So a class of a curve is integral. Above, it's I've said it could be round, and round is definitely not rational. So this is the statement of the cone theorem, as I will state it in a little bit. I want this on this side. And what I want to do is give you a suggestion of some of the ideas that go into the cone theorem and some of the conjectures that lie around it. So this is just the beginning of the investigation. Once you are here, that's okay. I think I managed to draw a picture that is. Thank you. So I want to give some of the ideas that go into proving that this is the structure, and some of the ideas that go into results and conjecture that go beyond. And the goal is what I want there, which is still conjectured, but major advances have been made recently. So here's the lemma. Let C be a curve of genus bigger or equal to 1. So let me just point out one thing. So I'm saying we are studying the birational geometry of higher dimensional varieties, but I want to kind of stress the point that the geometry that we understand is the geometry of curves. So we are studying using curves, and we are studying curves on the variety. Okay? So let C be a curve of genus 1. Let F be and B any curve with open subset B0 inside B. And so I'll draw a picture in a minute. So, and let F from C cross B0 be a map to X. There's one more thing I forgot to fix. I fix a point in C. So that F restricted to P, namely F from P cross B0 is constant. So this is B0 inside B, so I'll draw here what's added to B. So this is a kind of a missing piece of C cross B, and I have a map from the open piece to X. So this is X. So the open piece is B0, C cross B0. And here's my P cross B0, such that the image of this, so it looks like sort of like this. Okay? So that this point sort of maps to a point. Then I claim, so B any projective curve is open. Then I claim that, and assume f is non-constant. Then there is a rational curve what do I want to call it? Maybe gamma? Where is it? I didn't call it anything. Then there is a rational curve, gamma, inside X, such that f of p, which is, so this, I'll call this f of p, which is a little misleading. It's f of p cross B0, but that's fine. It says this is in gamma. So what I claim is that is again a point where, so here's the rational curve.
Suppose f factors from B0. That's so the constant. I mean, f is not constant.
Yeah. So non-constant, neither on a fiber and not on the. So f restricted to each fiber is non-constant, and okay. So assume the dimension of the image of f is 2. Do you believe me now? Okay. So why is this true? Let's think about it. Because of this condition that Franz now reminded me to add, so let's take so image of f is inside X, and I can take the closure of image of f, and there's some ample line bundle there. So f has some ample divisor, and I can easily choose D not to pass through f of p. Okay. Now the key point that in order to prove this lemma is to say that the map does not extend to a map from the product C cross B. So I mean, you need to prove a little more than that. So let's convince ourselves that C cross B, so there's no map C cross B to X extending this. Okay, so this is just an idea. Why is that? If I would be able to extend it to a map from C cross B to X, then I pull back the divisor D that does not map through F, not go through F of P, then the inverse image of the divisor D would look something like this, right? And it would not intersect P cross B. But on a product, the only divisors that have this property, only effective divisors are the inverse images from the projection to C. So it's pi sub C upper star of some other divisor on C. So it would be just a bunch of horizontal lines. And that's really impossible because such a divisor, I mean, a pullback of something from a two-dimensional variety has code area dimension 2, whereas this has code area dimension 1. So, I mean, there are various ways to say the same thing. Now, instead of course, this does not prove what I want. So where's the rational curve? In order to prove this, what I do is I extend this map, and I can, at least after semi-stable reduction, I can extend it to something, some other surface. After blowing up, I can always extend it to some other surface that does map to X. And by the theory of semi-stable reduction, the only component that I will see are the original curve C together with some chains of rational curves. Now, if I only had the chains of rational curves attached at points other than this point, I would still be able to repeat this argument and get a contradiction. So the only way I get away from this is if there is some blow-up process at P that is necessary in order to extend the map. And the image, after you blow up, of this rational curve, after all, you blow up points on a surface, you get rational curves. The image would be a rational curve that meets the image of P, and therefore it goes through the image of P. So that's this lemma. Now, Darmon does it much better. I will also need a little bit of an analog for rational curves mapping. So this is only for curves of genus bigger than 1. And of course, for rational curve, the theory of semi-stable reduction is different. So I need something different. So here's the lemma for rational curves. If you think about rational curves, what you need is 2 points mapping to. So lemma C is now P1, and B as before. And assume that I have F from C cross B naught to X such that the restriction to 2 distinct points is constant. And that the dimension of the image is again 2. And then so the claim is that the class of the curve breaks into 2 pieces. I'm not going. It goes either through one of the then there is then the class of f of c. Well, the class can be written as a class of C1 plus C2, where these are non-zero classes of rational curves in X. So the class is not irreducible, that's what I'm saying. Non-zero classes of rational curves. And I can also say that they pass through the one through one point and one to the other point, but that's not. So the picture is, instead of that, here's X. Here I have 2 points, and I have my rational points kind of bending, and at the end they'll have to break. And the proof is the same, you just have to be a little more careful. I haven't been careful anyway, so maybe I should just keep this picture up. So now a little bit of deformation theory. Luckily, after Wiles, you're allowed to mention deformation theory in a conference where number theorists sit. So there is deformation theory started, well, it has a long history in algebraic geometry, and in particular, you can, if you look at a space of all curves of a given class, you can estimate its dimension using cohomological methods, just as Wiles does later on. So suppose I have a map from a curve X, a morphism. Then I have for myself a summary here. And I have, let's say, k points on the curve. No, my notation is n. Then I want to estimate the dimension of the deformation space at this map F, which fix of those maps that fix the points P1 through Pn. And there's a simple cohomological argument that says that this is bigger or equal to the Euler characteristic on C of f upper star of the tangent bundle of X twisted by minus the sum of the points in question. And you can, by Riemann-Roch, you can write that down numerically. So Wiles was not the first one to do such things. This is a telling number. Well, I'm not done, of course, but so it's minus the degree of the canonical divisor class on X restricted to the curve, plus numerical, the usual things that come into. So dmax is just the rank of this vector bundle, and this is the degree. This is the usual Riemann-Roch. X was always a smooth projective variety. It was there. You don't see it anymore. So in particular, let's look at this lemma. I want to be able to say that maps that pass through 2 points have an image of dimension 2, and that will tell me that the curve will break in the rational curve case. So let's assume for the time being, for simplicity, that we have a Fano variety that, well, the time being is this lecture. So let's assume for the duration of the sketches of proofs that I'm giving you, that kx is ample. Otherwise, you need to you need to choose another ample bundle to be able to measure things with respect to it, and it's a little more technical, and I don't want to go through it. So let's take a rational curve and ask ourselves, what do we need in order to ensure that the class of this curve breaks? So say C is rational, and say minus kx dot c is bigger or equal to dmx plus 2, then this means that the dimension of the deformation f restricted to 2 points, it's minus so you just plug in there. G is 0, n is 2, so you have here minus dim x, and that's the minus dim x there, and this is the other term.
So minus x ample or x kx?
Minus kx is ample. Thank you very much. So let's assume that we have a chance of finding like in surfaces, minus 1 curves. This is absolutely crucial. You want to, so in some sense, varieties where kx is ample are varieties where you don't expect to blow down anything. You don't expect to contract anything. Like in the case of surfaces of general type, you take their minimal models. So we look at say this is ample. So we assume that this is so ample that it's bigger than this. Then this means that the dimension of the deformation space is at least 2. Now let's assume that C is not just, that we don't have just a map, but C is inside X. So in which way can a curve inside X, the map from P1 that embeds the curve in X, deform keeping 2 points? Well, there's still a C star, a GM, for the arithmetician. There's a C star moving the P1 fixing 2 points. Think about the points at 0 and infinity. You just rescale the curve. But that's just one dimension. And if the deformation space is two-dimensional, the curve has to move. So this means that the curve breaks as... Now, the reason I assume that minus k is ample is because minus kx is ample, each one of these is positive, so they're both positive, and now I have an inductive procedure. If I start with something with too big a degree, then I can break it. So what does this mean? What does this mean is that there exists so if there is a curve like this, then there exists a rational curve with minus kx dot c less than or equal to dmx plus 1. It has to be less than this. Okay, so this is part of... So remember this. So we still have the... So I want to claim that such a curve always exists. So how do you do that? And that's... So this is all, by the way, this is all work of Mori so far. A priori, on a projective variety, I don't know that I have a rational curve. What I do know is, because the variety is projective, is that there is a curve. I slice it with hyperplanes until I go down to a curve. So every projective variety has a lot of curves. In fact, the cone of curves is dual to the ample cone, so there have to be many, many curves. All right, so let C be any curve. All I need to do, so what the first step, this step above, tells me is all I need to do is produce a rational curve. Once I have a rational curve, I'll know that there's a small rational curve. I should just point out that under these assumptions, this minus kx dot c is strictly positive. So I actually have the curve completely under control. So I just need to find one rational curve. This is like a problem that we have been doing here, find rational points on varieties. So how do you, this is really spectacular. So let's see what that tells us. So the estimate on the, I want the image to be at least one-dimensional when I have 1 point. So let's put n equal 1 here by the first lemma. N equals 1, so this cancels with this. So I want, so C is again inside X, the curve in X. I want minus kx dot C, which I know is positive because minus kx is ample, minus g times dim x. And I want this to be bigger or equal to bigger or equal to 1. A non-rational curve, I cannot deform it within itself, so any deformation, if I have at least one, will push it out and the image will be two-dimensional. All right, so this term is really troublesome. If the curve were rational, we could think about taking a double cover and maybe compensate for having deformations of the double cover by having a lot of deformations. But if a curve is of genus bigger than 1, any branch cover, the genus will only grow. And if you do this exercise, you'll see that you'll never win. Never, ever win. So this is where a really spectacular idea comes in. Mori says that it was suggested to him by Hironaka. So, but, suggestion is not the same as proving a theorem. So the theorem was proven by Mori. So what this spectacular idea says is, you have a variety of complex numbers, a projective variety of the complex numbers. It can be defined over some finitely generated field, which you can spread over some finitely generated ring over Z, and then you can reduce mod P. Okay? The arguments of deformation work out fine. And when you reduce mod P, you can replace C by its Frobenius cover, which has the same genus. The Frobenius cover of a curve has the same genus, so I can form the curve Cm, which covers the original curve C by the mth power of Frobenius, when I reduce to, and I get a curve with the same genus, but since I have so the degree here is p to the m. So I have a cover of a curve by degree p. This is multiplied by p to the m. So I can make this as big as I want, and therefore I can make this bigger or equal to 1. So what does this say? Is if I reduce the variety mod P, and let's take the locus, those reductions which are still smooth and nice, and then this will deform, and there will be a rational curve modulo P. But those are so reduction mod P exists a rational curve Cp on xp, the reduction of x mod P. I'm being a little, this is a little sleight of hand. I need to choose a point on the spectrum of the ring of definition and so on and so forth, but you're all number theorists, you know what I'm saying. Okay, so there is a rational curve. So here's x, and here's xp. There's a rational curve here, a rational curve here, a rational curve here. For any reduction, so the fibers are, for any reduction I have a rational curve, but that's not enough. That does not mean that I have a rational curve over characteristic 0. What is enough is that I have a bounded rational curve. And that's where that's a crucial point, that I have a rational curve of degree, at most, the canonical degree is bounded. Rational curve, so minus kx dot Cp is positive. I can choose the reduction so that this is still ample for infinitely many p, and this is less than dmax. Now I can use the theory of Hilbert schemes that Grothendieck defined for us. So there's a Hilbert scheme parameterizing any bounded sort of curves. So this bounds the Hilbert polynomial of the curve, and therefore there's a finite type Hilbert scheme over spec of the ring of definition. Yes? Yeah, so originally, so the argument just says there is a rational curve. But I apply that argument again, the argument for rational curves. I found a rational curve of huge degree. But the argument for rational curves says that if there is a rational curve, there's one of bounded degree. It's not the same one. So the theory of Hilbert scheme says that I have these infinitely many rational points over all reductions on a single Hilbert scheme. Sorry. So the Hilbert scheme is not empty in all these reductions. But the Hilbert scheme is a finite type, so if it's not empty for all these reductions, then it has a generic fiber which is non-empty.
At least one component.
At least one component of that Hilbert scheme is non-empty. So if I look at the Hilbert scheme might have exotic components lying in characteristic P1, characteristic P2, and so on. But what this says is that there's a point, but this is a finite type, so there's at least one component of the Hilbert scheme that looks like this. And it has a generic fiber, therefore of the complex numbers, it has a point. I don't know that it has a rational point, but at least I know that after an extension, there is. So the generic fiber has a point. So what is that point? That's a class of a curve inside, a rational curve inside x of degree at most degree x plus 1. And now I can state the cone theorem, which luckily I left the picture. Maybe I'll state the cone theorem so that it will fit with that picture. The cone theorem, so you need a little more arguments when minus kx is not ample. You need to be a little more careful, but the cone theorem says that if x is a smooth projective variety, then there is a countable collection Ci of classes of curves Ci, where Ci are rational curves, and they are discrete in the so kx dot c is negative, and they are Ci is negative, and they are discrete in this half plane. Such that the cone of curves, any, can be written as the round piece, the kx positive piece, I'll write it this way, kx bigger or equal to 0, maybe with a q, plus this sum. I guess I did everything over q, and I might as well leave it. Plus the cone generated by this countable collection. So this is the cone theorem. So there's a side of the cone on which we have no control. The kx negative is locally polyhedral and generated by classes of rational curves. Okay, so now I want to state, so this is just one step in a minimal model program. Here's an important other theorem that you can prove. You take one of these Ci, and the claim is that these are like -1 curves in many respects. Namely, you can contract them. You can contract precisely those curves, each one at a time. So the contraction theorem says that the contraction theorem is that for every I, there exists a map from X to some yi. So this is a normal projective variety. Such that the relative Picard number is 1. Let me write it like this. It has rank 1. Whichever line bundle is ample on the fibers is okay, and such that maybe I should copy the theorem from what I wrote. So this is C. So I'll call the Q times Ci. This is the ray in the cone, a boundary ray, which is called Ri. It's called an extremal ray. So CRI, and what I'm saying is, this morphism has connected fibers. CRI has connected fibers, and moreover, I can tell exactly which curves are contracted. And a curve. What do I call that other curve? A curve D inside X maps to a point under this map CRI, if and only if the class of that curve is in this ray generated by CI. This RI. So, of course, if you contract the curve, you contract any multiple of that curve if this curve moves enough so that you can put the multiple. But, for instance, there are cases where you can contract a P2, and the generator of that thing is just a line in P2, but of course there are other curves in P2 which are equivalent to a multiple of the line. So this means that these extremal rays can be sort of killed one by one. And something happens when you do that. The Picard number is reduced exactly by 1. So now I can state the minimal model conjecture. I can state what this implies and what the and basically there are 3 cases. So one case is when this construction map, where the dimension of yi is smaller than the dimension of x, so there are fibers. Then this means that x is covered by classes of curves in the class of C. Well, you need to worry about it a little bit, but in fact, x is uniruled in that case. X is covered by rational curves. So this is sort of understood. There's a reason why kx was not positive. The second case is the dim yi, so dim yi equals dim x, and this breaks into 2 subcases. Case Roman numeral 1 is where the exceptional locus is a divisor. And then, well, I only know that yi is a normal variety, but the theory has been extended, although not as beautifully as what I've told you. There's no reduction to characteristic P and stuff like that. The theory has been extended, and in fact, you can continue. You can replace x by this yi and continue. The second case is the trouble case, is where exceptional locus the exceptional locus has higher codimension, is not a divisor. And in this case, it's just impossible to replace x by yi. Yi is way too singular. And what you do in this case is what's called a flip. So there was an extremal ray which was contracted, so minus kx dot ci was negative here. This is a small contraction as well. The exceptional locus is again small, and the curves that minus, sorry, not minus, kx dot ci is negative. Did I write minus where I shouldn't have? So minus kx dot ci was positive, so kx dot ci. So here kx dot ci this time is positive. So you got rid of some of the negativity. The only problem is that this is a conjecture. So this is in case 2, which says that conjecturally there's something else where you can replace x by x plus. And it's known in dimension 3. It's now known also in dimension 4. And is it known in dimension 5 by this Alexeyev, Kawamata? Or is this still, is it? Yeah.
That is a problem. You should assign a probability.
Okay, so there's a paper that I think basically says that maybe there's a small technical problem, but I think it's now known due to work of Shakurov, Haken, McKernan, and Alexeyev, Haken, and Kawamata that it works in dimension 5, I think. So what this allows you to do is finally get to a minimal model. Maybe I'll erase here. So this procedure, you start with your x, where kx was negative on something, and you start getting rid of these things where kx is negative on something, either by doing the contraction, if it's divisorial, or doing the contraction and finding a flip, if you manage to do that. And after finitely many steps, so conjecture, the procedure is finite. Which is kind of obvious if only contraction existed because you reduce the Picard number. In the flip case, you have to really work hard to show that this thing stops somewhere. So this is the termination of flips, and this is the existence of flips. And the conjecture is that this is finite, and you get to which says that some multiple of kx min has a base point free space of sections. Some big multiple, m times k x min, is base point free. This is called the abundance conjecture, and together, all this thing together is the good minimal model program, which implies in particular the minus infinity conjecture, implies semi-additivity of Kodaira dimensions, it implies a lot of beautiful things that I have suppressed. They are a little more prevalent in the notes than in my lectures. So I think this is a good time to stop.